Let's talk about pitch. We'll talk about how pitch arises mechanically, what gives a sound the sense of pitch, and we'll learn about our sensitivity to pitch. First of all, going back to acoustics, objects have modes of vibration. A mode of vibration can be thought of as how the object is bending or flexing, and I'll show you an example shortly. These different modes of vibration have characteristic frequencies, and in some cases these characteristics frequencies are approximately harmonic. An example is a stretched string where the modes of vibration are the fundamental mode, which is the whole string goes up and down like this. There's a second mode where the string vibrates like this, and beyond that I'm going to have difficulty manipulating my hands, but I think you can imagine a string vibrating in thirds and fourths and fifths. And in an ideal string, that means completely flexible, uniform, and so on, the frequencies of those different modes of vibration would have a ratio of 1 to 2 to 3 to 4, and so on. Modes generally decay exponentially. Sometimes is nonlinearity in, oftentimes there's nonlinearities that make things more complicated, can actually create some coupling between different modes of vibration, and so on. So I don't want to pretend like everything is really that simple, that all modes of vibration decay exponentially and behave like sinusoids. Here's an example of some modes of vibration. So this is the top of an acoustic guitar, and we'll see one mode of vibration illustrated graphically here. So obviously a great exaggeration. Let's look at the next one down here. So this is a different mode where instead of the entire surface of the guitar top moving together, parts are coming up while the other part goes down, and this would, I think, obviously be a higher frequency, higher mode of vibration. Okay, so something interesting happens when musical instruments are driven into oscillation, either by bowing or blowing. And we talked about this before, and forgive me for belaboring it, but I think it's so fundamental. I just want to make sure I get the point across. The feedback mechanism that sustains the oscillation results in periodic oscillation. So somehow all the different modes of vibration are locked together in phase somehow so that they become perfectly harmonic partials. In reality, there's always noise and jitter and non-uniform driving forces, etc. And so these complicate the picture a little bit, perhaps perturb the system from perfect harmonic oscillation. But the approximation that driven oscillators produce periodic harmonic spectra is a very good approximation. So we perceive vibrations. I'm not sure why we are so sensitive to pitch and harmonic partials, or why that's so important. It probably has something to do with evolution. The audio perception of cats has been extensively studied in the lab, and cats have many of the same structures that humans do in terms of perceiving harmonics. So our sense of pitch is strongly related to frequency. Higher frequencies mean higher pitch. Our sense of pitch is enhanced by harmonic partials. In fact, the connection is so strong that we are unable to hear individual partials in most cases. We tend to collapse all of those partials into a single tone and assign a pitch to that, which is the fundamental frequency of oscillation. Pitch perception is approximately logarithmic, meaning that when the pitch doubles, you hear a certain pitch interval. When it doubles again, you hear more or less the same interval, even though now the frequency is 4 times as high instead of 2 times as high. This factor of 2 is actually very salient in our perception of pitch and has a name called the octave. If we take this factor of 2 in frequency, called the octave, and we divide it into 12 logarithmically spaced intervals, those are called musical semitones or half steps, and that is the basis for most Western music. In this picture of the keyboard over here on the right, the interval from one key to the next, like going from this white to black to white to white, black, white. And each one of these intervals is a half step or a semitone, and 12 of those represent an octave, as you see here in the figure. If we take each semitone and we divide it into 100 logarithmically spaced pitch intervals or frequency intervals, those are called cents. And often cents are used in the measurement of perception and studies about intonation. Musicians use cents. They'll say, one performer seems to be 10 cents sharp or 20 cents sharp or something. We're sensitive to about 5 cents, and I have a little example here of an interval of 10 cents. You might be able to hear a very, very slight pitch change between those two tones, and you may or may not be able to hear which one is higher than the other. We're pretty close to the limit of hearing, but that's 5 cents. The interval between 2 notes on a piano is 100 cents, and we hear that. What I'd like to do in this sound example is play a musical scale of 1 octave, and then I will play some 1 octave intervals, just so you can hear what an octave sounds like. So notice in that last example there were the same, what we call a pitch class being played in different octaves. So we took the low note, doubled it again, doubled it again. We went up and down in octaves, and then that example went up 100 cents, and we played many different octaves again. And the overall perception probably was that you heard something, and you heard that was kind of all the same, just different octaves of the same pitch class. And then it went up a half step. And so the fact that we can sort of identify all these different octaves as variants of the same thing is very interesting. That's why octaves are so important and that we have a name for it. Here's another illustration of the octave. I have one tone that is steady. Another tone is sweeping up to exactly 1 octave above the first. And there's a very strong sense of resolution, or finding a place or coming home when that octave is reached. So we can listen to that. Okay, so I hope you heard that lock in through the magic of streaming video. You can listen to that as much as you want, or any of these other sound examples.